Superconductivity occurs in a large number of metals, alloys, and compounds. There seems to be no simple definition for superconductivity. Rather, we deal here with a complex group of phenomena. The superconducting state doesn't even seem to be the same in all the materials in which it has been found to exist. Thus, there are the so-called type 1 and type 2 superconductors. It will not be possible to touch in this film on all matters of interest. In our experiments, we will be using superconductors of type 1. These are easier to describe and more completely understood at the present time than the others. However, two properties are common to both types of superconductors. One is that the temperatures involved are low. The transition temperatures between the normally conducting and the superconducting phases lie close to the absolute zero. Of course, these transition temperatures vary from one material to the other. Yet, in most cases, liquid helium is required as a cold bath to produce superconductivity. The second property shared by all superconductors is perhaps the most striking. Their electrical resistance suddenly drops in value at the transition temperature. Not only does the resistance drop in value, we have every reason to believe that it goes to exactly zero. We can now make perfectly conducting circuits. Circuits in which currents persist over great lengths of time without measurable decay and requiring no external electromotive force to maintain them. Now, perfect conductivity is only one aspect of superconductivity. Superconductors exhibit striking magnetic properties as well. One of the most significant of these is the so-called Meissner effect. We'll study it in some detail later. But to begin with, we'll measure resistance in a piece of wire at very low temperatures. I have here a length of tin wire wound over a plastic cylinder. Two copper leads have been soldered to each end and rise upward through here. We will use this wire in a brief series of experiments of increasing precision to show you that the resistance of tin is immeasurably small below a certain temperature. The wire has been put into the inner vessel of a double vacuum bottle or double dewar. The outer dewar surrounds the inner one and is filled with liquid nitrogen. There is liquid helium in the inner dewar. The two vacuum jackets, together with a layer of liquid nitrogen between them, provide thermal insulation for the liquid helium in the inner dewar. The normal boiling temperature of liquid helium is about 4.2 degrees Kelvin. That's roughly 269 degrees below zero centigrade. The cover over the inner dewar is at present open through this port. The pressure in there is atmospheric. So the temperature of the liquid, and therefore of the tin wire too, is 4.2 degrees Kelvin. The leads from the tin wire rise out of the dewar through a simple seal. One lead from each end is connected to a battery in series with a switch, a rheostat, and an ammeter. The other pair goes to a millivoltmeter. A current of 1 ampere creates a potential drop of about 25 millivolts across the tin wire. Its resistance is about 25 milliohms. So, at 4.2 degrees Kelvin, tin is a normal conductor. First, we want to cool the sample of tin wire. This we do with a vacuum pump over there. It connects through valves, closed at present, to the inner dewar, which will be vacuum tight as soon as I close this port with a rubber stopper. The pump carries off helium vapor. Evaporation will cool the liquid remaining behind, and therefore the wire too. Secondly, we want to keep a record of the potential drop across the tin wire as the cooling proceeds. To get such a record, we remove the millivoltmeter and we replace it with this recording instrument. It is a so-called XY recorder. The horizontal, or X, motion will be so used as to indicate the lapse of time as cooling proceeds. The vertical, or Y, motion is connected to the voltage lead from the tin wire. It is calibrated in millivolts. We again set the current to 1 ampere. This deflects the recorder to 25 millivolts. The temperature of the wire is still about 4.2 degrees Kelvin. Next, we set the recorder pen down on the graph paper and start the horizontal sweep, indicating elapsed time. The current in the wire is held constant at 1 ampere. The potential drop in millivolts and the resistance in milliohms have therefore equal numerical values. This is the superconducting transition. As you can see, the resistance has dropped to 0 within the limits of accuracy of this instrument. The recording voltmeter has been used to just about the limit of its sensitivity. We now replace it with this high-gain DC amplifier. It will be used as a microvoltmeter. The small voltages to be measured are applied here. The amplifier output is measured on a Darson-Wahl meter, which is bidirectional with its 0 at the center. We select the range in which full-scale deflection to the right or left signifies an input voltage of 1 microvolt. The liquid helium has been cooled below the transition temperature of tin. Let us measure the liquid's temperature. To do so, we use an accurate pressure gauge which is connected to the vapor space above the liquid surface in the inner dewar. The needle registers the pressure there. It is the saturated vapor pressure of liquid helium. The corresponding liquid temperatures are well known, and the gauge is already calibrated in terms of these. The liquid helium is at 1.6 degrees Kelvin. The voltage leads from the tin wire in the dewar are connected to the microvoltmeter input. The voltage across it is 0. There is no current in the tin wire. As the current goes to 1 ampere, there is a sudden voltage surge of about 1/10 of a microvolt, and then the voltage returns to 0. The surge is a small electromotive force due to the self-inductance in the circuit. Breaking the circuit causes the current to collapse and an opposing self-induced EMF, as it should. The result important to us here is that after this transient, the potential drop is 0 again, while the current is 1 ampere. Remember that at this current, above the transition temperature, the voltage was 25 millivolts. It is now 0 to within the estimated error of this scale, which is about 1/100th of a microvolt. The voltage across the wire is not more than 1/100th of a microvolt while it is superconducting. Above the transition temperature, it was 25 millivolts. Therefore, the resistance of the wire has dropped on transition by a factor of 2.5 million or more. We have fashioned a ring out of tin and placed it into liquid helium. The ring hangs from a thread which provides little torsion. By a simple electromagnetic method, we have induced a current around the ring. To prove the existence of this current, we bring a magnet to the dewar. The current in the ring gives it a magnetic moment, and it oscillates in the external field of the bar magnet. Remove the magnet, and the oscillation disappears. Reverse the bar magnet, and the ring turns around. Such current-carrying rings of tin or lead have been kept in a cold bath below their transition temperature for months and even years. In all this time, the current kept flowing. By measuring the magnetic field of the current periodically, it was possible to show that the current does not decay measurably at all for periods of years. In this way, and in other ways, it has been proved that during the superconducting transition, resistance drops by a factor of 10 to the 20 or more. We now believe the resistance becomes zero. We call this state of the metal superconductivity. The current in the ring is called a persistent current. In our next experiment, we measure the temperature at which tin becomes superconducting. We will use our microvoltmeter to detect the transition. Because it is very sensitive, we need only a small amount of current in the tin wire, and the wire need not be as long as the one which we used before. 2 copper leads have again been soldered to each end. One pair carries the current, and the other pair is connected to the voltmeter. The tin wire is now in the liquid helium at a temperature of 4.2 degrees Kelvin. Here is a composite picture of our equipment. The current in the wire produces a potential difference. The wire is in the normal state. We are cooling the wire with a vacuum pump as before. The voltage is just now dropping to zero. This is the transition. We are marking the corresponding temperature on the thermometer. Our value for the transition temperature of tin is 3.71 degrees Kelvin. More precise measurements put it at 3.722 degrees. We've shown that superconductivity is a state of zero electrical resistance, or, to put it the other way around, of infinite conductivity. Although this is remarkable enough by itself, superconductivity is quite a bit more than that, as I mentioned at the start. To show this to you, we now go on to new experiments. They will involve magnetic fields. To begin with, we again measure the transition temperature of tin using the short sample of tin wire. But this time, we've put it parallel to the magnetic field of this electromagnet. For the fields at which we shall be using the magnet, its flux is proportional to the coil current. There is an ammeter in series with the coils. It is already calibrated in terms of the flux density prevailing in the central region between the pole pieces. The field at the wire is 80 Gauss. The same current which we used in the previous experiment is again flowing through the wire, and it registers the same IR drop on the microvoltmeter. Clearly, the tin sample is in the normal state, but notice that its temperature is already much lower than 3.71 degrees Kelvin. This was marked off in the previous experiment as our value for the transition temperature of tin in the absence of an external magnetic field. As you can see by the motion of the thermometer needle, the temperature is falling. We are pumping on the liquid helium. Keep your eyes on the microvoltmeter. There. At 80 Gauss, the transition temperature of tin is 3.12 degrees Kelvin. The field is still at 80 Gauss, but the sample has been cooled to 1.5 degrees Kelvin. The sample is superconducting. We are increasing the magnetic field while keeping the temperature fixed. In the neighborhood of 250 Gauss, the field destroys the superconductivity of the sample when its temperature is 1.5 degrees. We call it the critical field for the temperature in question. At fields exceeding the critical value, the superconducting state cannot exist at a given temperature. We have discovered an important property. It is this: magnetic flux density is a state variable in superconductivity. Let us plot the three transition temperatures and associated critical flux densities. By measurements similar to those we have performed, one finds that the critical flux density depends upon the transition temperature in roughly parabolic fashion. The parabola has its vertex at absolute zero. Points above this curve signify normal, points below it superconducting states. All superconductors show this type of behavior in magnetic fields. The value of the transition temperature will vary from one material to another. There is a maximum critical field B0 for every superconducting material. At fields whose values lie above B0, superconductivity cannot exist. Below B0, the value of the field strongly affects the transition temperature. These results would seem to indicate that the superconducting transition might involve more than a change from finite to infinite conductivity. The external magnetic field influences the temperature at which this transition occurs. Therefore, it seems natural to ask whether the magnetic properties of the material don't also undergo a change. As a matter of fact, the laws of electricity and magnetism have something to say about magnetic fields in materials with infinite conductivity. Let me explain it the following way. As we have seen before on our voltmeters, there can be no potential difference between 2 points in a material with infinite conductivity, even if a current is flowing through it. So, the potential has the same value at all points. This means that the electric field intensity is zero. It also means that no electromotive forces whatever can exist in the material. In particular, consider the induced electromotive force which would exist around circuits whenever the magnetic flux is changing with the time, as we know from Faraday's law of electromagnetic induction. But in our material, no such EMFs may exist. Therefore, the magnetic flux cannot change with time in the material. To put it succinctly, the magnetic flux density cannot change with time in a material of infinite conductivity. Any magnetic flux which resides in it while it has infinite conductivity is frozen to it as long as it has infinite conductivity. We now wish to find out by experiment what actually does happen to magnetic flux during the transition from the normal to the superconducting state. For this purpose, we'll put a tin cylinder into the liquid helium with its axis at right angles to the field of the electromagnet. In its median plane, we position an array of many small compass needles. As you can see, the needles are free to turn and tend to align themselves parallel to the magnetic flux they see. Our device is in the dewar. The tin sample is normal and the flux density is 80 Gauss. The needles are oriented parallel to the magnetic field. This indicates that the magnet's flux is essentially unaffected by the presence of the cylinder and permeates across it unaltered in density. As a matter of fact, the permeability of the superconducting materials in their normal states differs very little from unity. The failure of some needles to point horizontally is not due to the magnetic properties of the cylinder, but to their own small magnetic fluxes and mutual interactions. Our next step is to cool the tin cylinder into the superconducting state while holding the magnetic field constant. It so happens that this transition takes a considerable length of time with the experimental setup we have here. For our large cylinder in a field of 80 Gauss, a good deal of heat must be carried off before the transition is complete. Now, we do this by pumping off helium vapor, and the heat of vaporization of helium is quite small. In fact, the transition proceeds so slowly that we are showing it to you at 6 times normal speed. Notice that the compass needles are turning. The directions they are taking on show that the magnetic flux is coming out of the cylinder. We are witnessing here an effect of fundamental importance in superconductivity. Magnetic flux is ejected during the transition to the superconducting state. It's called the Leitner effect and occurs in all superconductors. There is one special group of superconductors which, under ideal conditions, eject all the flux during this transition. Tin and most of the other metallic elements exhibiting superconductivity belong to this group. They are called type 1 superconductors. The effect is then called the complete Leitner effect. It should be emphasized that this demonstration does not in itself prove that the magnetic flux is completely excluded from the cylinder. It could be partially excluded and show roughly the same exterior flux configuration. In tin and in all other type 1 superconductors, the flux density B is identically zero under ideal conditions. This could not be predicted from the knowledge that the material has infinite conductivity, or that, to say it another way, the electric field is zero in the material. As we saw earlier, the fact that E vanishes requires only that B may not change with the time. So we must consider the Leitner effect as a separate and independent phenomenon of superconductivity, consistent with, but not a consequence of, infinite conductivity. In our next experiment, we want to demonstrate that the Leitner effect in tin is complete. We've wound some insulated copper wire into a coil of several hundred turns directly on a piece of tin. The coil senses changes of magnetic flux in the cylinder. The terminal leads will come out of the dewar through this tube. The cylinder is placed in the dewar with its axis parallel to the field of the electromagnet. By Faraday's law of induction, any time rate of change of magnetic flux through this coil induces an electromotive force. The rate of change of flux multiplied by the number n of coil turns is numerically equal to the EMF induced in the coil. Therefore, the time integral of this voltage is a measure of the change of flux during a given time interval. In our experiment, this voltage integral, or voltage impulse, will be about 4/10 of a millivolt second. To record the time integral of the induced voltage, we use this instrument. It is a digital integrating voltmeter of very high voltage sensitivity. The time integral of input voltage will appear on the dial in millivolt seconds with a decimal point here. The cylinder and coil are in liquid helium above the transition temperature for tin. Our plan is first to turn on the magnetic field while the tin cylinder is in the normal state and to record the voltage impulse. Then, while keeping the field constant, we cool the cylinder through the superconducting transition and again measure the voltage impulse. We are slowly turning on the magnetic field up to a flux density of 40 Gauss. The dial records corresponding voltage impulse, which is the measure of the admitted flux. Its final value is plus 0.401 millivolt second. We record this value and set the meter dial back to 0. Now we begin pumping on the liquid helium. as you can see by the increased rate of boiling. This cools the thin cylinder. During all this time, the current in the coils of the electromagnet is being held constant. A negative voltage impulse is piling up, indicating the onset of the superconducting transition. The final reading is a measure of the flux excluded from the tin cylinder during the transition. It closely equals, in numerical value, the reading which measured the flux initially admitted by the cylinder in its normal state. We filmed this experiment 11 times. The average of the measurements of flux admitted in these 11 runs exceeded the average of flux ejected by several %. The average deviation of the measurements was such that the ranges of possible values overlapped. We have taken the liberty of showing you the best of these 11 runs. We can draw a number of conclusions from the discovery of the complete Meissner effect in type 1 superconductors, such as tin. Let me emphasize one of them, that if such a material is in the superconducting state, electric current can flow only on its surface. If there were a current in its interior, it would have to be accompanied by magnetic flux. Yet, in our superconductors of type 1, B must vanish at interior points, so current can flow only in the surface. Actually, however, there is a layer of finite thickness, called the penetration depth, in which these supercurrents flow. It is of the order of several hundred angstroms deep under most conditions. We can now explain what happens when the tin cylinder turns superconducting in an external magnetic field. Supercurrents form and flow on its surface in such a direction that their own flux cancels that of the external field inside the material. They also affect the exterior in such a way that the net effect is total flux expulsion. They are called shielding currents. They encounter no resistance and remain as long as the field remains, or as long as the sample remains superconducting. If we have a tin ring in its normal state and in the field of a bar magnet, the magnet's flux penetrates through the ring as well as through the hole in it. When the ring is cooled into the superconducting state, shielding currents are created which eject all the flux from the tin itself. As long as the ring is superconducting, that flux of the magnet which laces through the hole cannot cross outward through tin. It is trapped. Here you see the ring in the Dewar. It has been cooled in the presence of a bar magnet. The flux density at the ring is roughly 50 Gauss. The temperature is about 1.5 degrees Kelvin. The ring is superconducting. Since the flux is trapped, removal of the magnet induces a current on the ring's surface such that this current now accounts for all the flux that cannot leave. Its sense and its value is consistent with Lenz's and Faraday's laws. The current encounters no resistance. It remains as a persistent current, as we have seen once before. A small bar magnet is brought down toward a lead cup whose temperature is 4.2 degrees Kelvin. The superconducting transition of lead occurs at 7.2 degrees in zero magnetic field. Even in the field of the magnet, the bowl remains superconducting at 4.2 degrees. Supercurrents are set up on the surface of the bowl, which shield the lead from the flux. They are induced electromagnetically, and by Lenz's law, the magnet is repelled. It floats above the bowl. In the superconductors, we are dealing with a quantum mechanical state which dominates the electrical and magnetic properties of the solid in the bulk. Our next experiment will shed some light on the nature of this state. It turns out that the conduction electrons become bound to each other during the superconducting transition. I have on this glass slide what is known as an electron tunneling junction. The metallic cross was laid down in 3 steps. First, a thin film of aluminum was deposited on the glass by the technique of evaporating metal off a hot wire under vacuum. This film was then restored to the atmosphere at room temperature. This produced a thin film of aluminum oxide over the aluminum film. Finally, another metal film was evaporated crosswise over the oxide layer. The second metal film is lead. The oxide of aluminum is a non-conducting substance, a dielectric. At the junction where the 2 metal films lie above each other, it separates them. We are justified in thinking of a parallel plate condenser. If we apply a voltage between the metal films, or condenser plates, we would expect, in terms of elementary classical physics, the little condenser to become charged, and that is that. Only if the voltage were high enough to produce breakdown in the dielectric should we expect an appreciable flow of current across the oxide. We apply a source of variable voltage across the junction. A voltmeter is connected across the junction from the other side. What we wish to test is whether a current flows when voltage is applied. If the voltage produces current across the junction, it could be detected if a resistor were inserted like this. Then, if there is a current, the IR drop between terminals A and B will be proportional to it. We shall apply these terminals to the y-axis of an XY recorder. The junction voltage will be applied to the x-axis. The junction is in the dewar. The temperature of the liquid helium is about 4.2 degrees Kelvin. The junction is above the surface of the liquid, and at a temperature sufficiently above 4.2 degrees Kelvin, so that both metal films are normally conducting. In zero magnetic field, the transition temperature of lead lies at 7.2 degrees. For aluminum, it lies at 1.25 degrees. The voltage axis is calibrated in millivolts. We set the recording pen down on the paper and now apply a slowly increasing voltage to the junction by sliding the potentiometer tab on the potential dividing resistor. As you can see, application of the voltage is accompanied by current. In fact, the relation of voltage to current is linear. Even at microvolts, this curve would show the same slope. The junction does not act like a condenser at all. How does the current get across the oxide? The explanation for it is quantum mechanical. Electrons are free to move around in each of the 2 layers of metal, but the oxide layer is non-conducting and presents a barrier. Speaking in terms of classical physics, electrons headed for the oxide layer are reflected if they don't possess enough energy to overcome the height of the potential barrier which the oxide represents. They can cross the oxide layer if their energy exceeds the barrier energy. We might call this dielectric breakdown. But quantum mechanically, a particle may cross a potential barrier even if its energy is less than the height of the barrier. This process is called tunneling. It is due to the fact that a moving electron, like all particles, has wave character. We may consider a group of electrons in the lead layer heading for the oxide as a wave beam. The broken line represents electrons of a given energy. The wavelength is given by their momentum. The amplitude represents the number of electrons at that energy. As a disturbance of this kind, the electrons may penetrate the oxide layer. But since their energy is less than the barrier potential, they cease to be wave-like in this layer. Rather, the disturbance decays. At the other side, a low amplitude disturbance, a wave again, of the same length and energy can be joined to this line. The low amplitude signifies that only a fraction of the electrons can tunnel through. The thinner the barrier, the more will tunnel. Keep in mind that in our junction, the oxide layer is very thin. Now, as we've told you before, there are electrons in each of the two metallic layers which are free to move around. These electrons occupy a certain set of closely spaced energy levels. If the temperature is close to the absolute zero, then, to a first approximation, these levels are occupied only up to a certain maximum energy level called the Fermi energy. The Fermi energy is not, in general, the same in different metals, considered separately. But in the junction we have here, the metals are in contact through the oxide layer via the tunneling process. Tunneling does take place, and so a net number of electrons moves from one side to the other until the highest occupied levels equalize. At this point, no further net exchange of tunneling electrons will occur. A consequence of this transfer of electrons is to raise the electrical potential of one metal layer and lower that of the other. The difference in potential is called the contact potential. Next, let us suppose that we apply a slowly increasing voltage across the junction from the outside with the help of a battery. This is exactly what we did in our last experiment. It further raises the energy of each electron on one side while lowering the energy of the electrons on the other. Now we can see why, in our last experiment, a current flowed through the oxide layer when a voltage was applied across the junction. Tunneling occurs and continues as long as the voltage is applied. Electrons tunnel and occupy empty, excited levels on the other side. The external battery removes them again, and others tunnel into their places, and so on. We now repeat the tunneling experiment, but this time we will do it at 1.5 degrees Kelvin with the junction submerged in liquid helium. At 1.5 degrees, the lead film is superconducting. The aluminum film, however, remains a normal conductor at this temperature. As a matter of fact, we are using it here only as an ordinary conductor. Aluminum was chosen because it is easy to evaporate it from a hot wire in vacuo, and because it forms a strong and thin aluminum oxide layer when restored to air. Again, we apply a slowly increasing voltage to the junction, which is now at 1.5 degrees. Notice that now hardly any electrons tunnel through the junction until, at about 1.25 millivolts, a sharp rise of current occurs. Are we to believe that the oxide layer becomes a perfect dielectric, allowing no tunneling, when it was cooled from above 7 to 1.5 degrees Kelvin, and that it broke down when the condenser was charged to a value of about 1.25 millivolts? The answer is, of course, no. One can show, in fact, that the properties of the oxide were not appreciably altered by this cooling, whereas we do know that the lead film changed from a normal to a superconductor. As we've shown earlier, this is the condition of the energy levels on either side of the junction when the lead is normally conducting. However, when the lead turns superconducting and an increasing external voltage is applied, there is no tunneling until this voltage reaches about 1.25 millivolts. Hence we conclude, in the lead layer, there are no energy levels available at first. That some energy levels are forbidden to the electrons in the lead after it makes its transition to the superconducting state. To put it in another way, there is a gap in the electron energy levels for superconducting lead. When we apply an increasing external voltage now, there will be, at first, no possibility for tunneling until the voltage is large enough to bring occupied levels opposite unoccupied levels. Then tunneling current flows and will continue to do so as long as we apply this external voltage of sufficient size. As we have seen in our experiment, the minimum required voltage is of the order of millivolts. Such energy gaps have also been found in most of the other superconductors. In all cases, they are small and of the order of milli-electron volts. In the normally conducting state of a metal, the conduction electrons behave like free particles. That means they behave as if they were free from each other. The strong Coulomb repulsion between any two of them is screened out by the aggregate of all the other electrons. Behavior like free particles also means that the electrons are not bound by the positive ions of the metal's crystal lattice. In the superconducting state of a metal, we find a gap in the electron energy levels. Now, this indicates that the conduction electrons have bound states. The smallness of the gap signifies that the attractive force which binds them is weak. We may rule out a binding force which holds the electrons to the positive lattice ions. If that were the case, the material would, like insulators, have high resistance. But we know that the superconductors have zero resistance. So we conclude that the electrons are bound to each other. Although the last word may not yet have been spoken, the most successful model proposed so far assumes that the electrons become bound as pairs. This has in fact been experimentally proved in lead and in tin. It was shown that the magnetic flux trapped by superconducting rings is quantized. The rings used were very small, and the quantum of trapped flux was actually measured. Its magnitude clearly indicated that its carrier is an electron pair. Now, the electron has spin quantum number 1/2. Consider a quantum mechanical system of particles with half-integer spin. The Pauli exclusion principle then requires that each particle of the system must be in a different quantum mechanical state. This is just what we believe to be the case for the conduction electrons in the normal metal. On the other hand, the requirement does not apply to a system of particles whose spin quantum number is an integer. In that case, there is no limit on the occupation number of each possible state. In the theory of superconductivity based on bound electron pairs, it is shown that the most likely pair to form is that one in which the paired electrons have opposite spin. So, a pair has zero spin, and even zero is an integer. In other words, a pair in some way behaves like a particle of integer spin. This line of reasoning makes the pairing of electrons a plausible model for superconductivity. Let me put it this way. Suppose that in a piece of metal, the conduction electrons tend to become bound in such pairs. Then, if the temperature of the metal is sufficiently low, these bound pairs may form, in macroscopic numbers, into a giant quantum mechanical many-particle state of low energy, which may extend over the whole sample. From this point of view, the superconducting phenomena, some of which we showed you earlier, become the observable properties of this state. One proposal for the nature of the force which tends to bind conduction electrons to each other in a metal is the following. It involves the lattice of positive ions. Now, this lattice is not perfectly rigid. The negative charge on a passing electron can start a vibration in nearby positive ions. The electron moves swiftly by, but the ion is heavy and vibrates relatively slowly. A little later, a second electron passing the vibrating ion is affected by this local elastic distortion of positive charge. If it arrives at the right phase of the vibration, the force on it will be, in effect, an attraction toward the first electron. The theory based on this model has had considerable success in explaining properties of superconductors.